Okay, so the title of my talk is Airy-beta line ensemble. But before I start, let me thank the organizers for this beautiful conference. It's always a pleasure to visit IPAM, and especially for this community. So let me give a preview of main result to set up the stage. What are the topics of my talk? So I will be reporting on our joint paper with Jiaming Xu, who is now in Sweden and will be in Ohio next year, and Lingfu Zhang, who is kind of local, working at Caltech currently. This theorem, if you want to put it in short, it says that rescaled largest eigenvalues of time-evolving self-adjoint random matrices converge as n goes to infinity to the single universal object, which is called Airy-beta line ensemble. And I don't expect that you understand all the words right away, so the point of the talk will be to explain in more details what this theorem is about and what is Airy-beta line ensemble, what it is. Okay, so let's start with a little bit of a background. So, many people arrive to random matrix theory through their own paths. So, there are many origins of this research area. So it comes from study of classical groups and their representation theory. It comes from statistics. It comes from theoretical physics, number theory. If you want to analyze ChatGPT, there's also something about matrices. So many reasons to be interested in random matrices. Now, no matter from what direction you come, there's a single object which somehow inevitably will show up as a Bayesian building block in any directions. And this object is called Gaussian beta ensemble. And let me on the next slide try to define for you this Gaussian beta ensemble, because many of my results will be really about this fundamental object. So what is Gaussian beta ensemble? So you take n times n matrix X with IID, real complex of quaternionic mean zero entries. And then you try to make a symmetric matrix out of it. So how do you do it? The simplest way is just to add to your matrix its transpose conjugate, divide by 2. Now you get a self-adjoint matrix M. So there is a self-adjoint random matrix. So it has a spectrum, which is real random variables, because all the eigenvalues are real. So you look at this real spectrum, and you can try to write down the distribution of the eigenvalues of this spectrum. And there is a certain miracle of exact solvability here, that for this particular Gaussian ensemble, actually the distribution of eigenvalues is very explicit. So it's given by this nice formula. So product xj minus xi raised to the power beta and product of exponent minus xi squared coming from the Gaussian potential. Well, you should treat it as a miracle, because in general, if you specify the law of matrix elements of a matrix, it's very hard to write down anything explicit for the eigenvalues. It's only for very special situations where you're able actually to write explicitly distribution of eigenvalues. Now, when you look at this formula, you can notice that, interestingly, the dimension on where you deal with real complex or quaternionic entries is very mild. It's just this parameter beta, which xi minus xj being raised to this parameter. And in particular, you can take this formula and you can extend the definition of this ensemble from these classical betas 1, 2, and 4 for arbitrary real values of beta. And in the terminology of statistical mechanics, and in this situation, beta will be called inverse temperature, because in statistical mechanics, what is very often happening is that you have distributions of this type exponent of 1 over t times something. And so this 1 over t, beta has role of this 1 over t, where t is a temperature. So in statistical mechanics, you would call beta inverse temperature. Okay, so these ensembles exist in this way for any values of beta. And this is what's called Gaussian beta ensemble. We will not be interested in Gaussian beta ensemble per se. Instead, we will be interested in two-dimensional extensions of this ensemble. We kind of want to keep in mind that the matrix is not one-dimensional object by two-dimensional object. So we want to add second dimension to our eigenvalues. And there are several ways to do it. So the first way, well, maybe my favorite, that's by looking at what's called Gaussian beta corners process. So what is that? So we start with exactly the same matrix M. But now, instead of looking only at eigenvalues of the full matrix, we'll also cut principal corners out of this matrix. And we'll look at the joint distribution of all these corners together. So maybe you have 4 times 4 matrix. You write the eigenvalues of this 4 times 4 matrix here. Then you cut 3 times 3 corner. You write these eigenvalues here. You cut 2 times 2 corner. These 2 eigenvalues, 1 times 1 corner, the last remaining eigenvalue. Now, linear algebra can be shown to, can be used to show these inequalities between eigenvalues. For example, this second eigenvalue of 3 times 3 matrix is exactly between second and third eigenvalue of 4 times 4 matrix. And altogether, not hard to, good exercise actually if you never So these eigenvalues to try to prove that that's what's true. Okay, now we are interested in these eigenvalues as random variables. So we already know that the full matrix, its eigenvalues of the full matrix have this distribution, but now we want to extend it and do this computation to compute joint distribution of everything. And that's another miracle happening here, that this is still explicit. So we still can kind of compute interesting Jacobian of transformation from from our matrix into these eigenvalues and get this formula, which says that the joint law of all these eigenvalues together is given here. So there is this factor in front row, which is very similar to what we had in Gaussian beta ensemble. And that governs kind of the top row eigenvalues. And then for other rows of eigenvalues, well, there are interactions between those. So eigenvalues will interact inside each row by the xi minus xj raised to the power 2 minus beta. And in addition, eigenvalues on the adjacent rows will also interact by these xi minus xb, where xa belongs to level k and xb belongs to level k plus 1, and this distance will be raised to the power beta over 2 minus 1. So nice computation, which you do again for beta equals 1, 2, and 4, for real matrices, for complex matrices, for quaternionic matrices, and you noted that you get kind of exactly the same formula. Well, modulo this beta changing to be 1, 2, 4, and then, okay, nice. So you look at this formula and say, well, this is again, you can extend it to any values of beta. This density clearly makes sense for any values of beta, and that will be one of our central objects, this Gaussian beta corners process, which by definition then is just this object, this interlacing array with this probability distribution. So that's one way how you can add second dimension to matrices. There is another way which may be similarly natural.
I have a question. When beta equals 2, does all the interaction term disappear?
Yes, so all interaction term disappear. So what happens is beta equal 2 is that conditionally on the eigenvalues on the top level, the rest is uniform, but subject to this interlacing condition. So kind of interlacing condition create for you finite volume polytope, and you kind of have uniform point on this finite volume polytope. Other questions? Okay, so beyond these extensions, there's another very meaningful extension, which we already heard about in this conference. But actually, before going to that, let me give you a little bit of motivations why you might be interested in these corners. So they appeared in many areas of mathematics, maybe historically the first appearance of this idea that you need to cut corners from the matrix was where people were looking into recurrences of various objects. There are special functions which are defined as all types of matrix integrals. And then when you want to compute these integrals, naturally you want to compute them by induction. And then this induction will be essentially boiled down to understanding the joint distribution of these corners. Another reason why you might be interested in corners is that they give you some kind of a nice parameters on the orbits of all matrices under orthogonal conjugation. So maybe you look at the real symmetric matrices, the orthogonal group acts on that by conjugation. There is an orbit of this action. You want to introduce some parameters. And these eigenvalues of this corner, there is a nice set parameters on these orbits. So this Gaussian corners process, it actually appears also as an answer in an interesting classification problem from ergodic theory. So when you try to classify all measures on infinite Hermitian matrices, which would be invariant under conjugations by infinite unitary matrices, you classify all these measures, and the answer turned out to be these Gaussian beta ensembles, Gaussian beta corners process. And also these corners process, they appear as limits of models of two-dimensional statistical mechanics, such as Tiling's and six-vertex model. So people saw them in various areas of mathematics. Okay, so alternative way how you can add dimension, also very natural one, is that you take your matrix and you think about your Gaussian matrix elements as just fixed time distributions of Brownian motions. And you say, okay, instead of looking fixed time distributions, let's look at the full time evolution. So now the matrix is starting to evolve in time, and you kind of keep in track of this entire matrix. So all matrix elements are independent Brownian motions. Alternatively, you can say that at integer times, your matrix is just a sum of independent copies of the matrices from previous slides. And then, you have this time evolution, and you try to project it onto eigenvalues, and you try to see what's happening with that. And it's a computation which goes goes back to the work of Dyson in 1962. What Dyson found is that if you project eigenvalues onto eigenvalues, that you get a Markov process which solves a very explicit SD. Well, so there are interactions between these particles which are inverse proportional to the distance. Well, there are Brownian motions which are driving this SD. And beta parameter is, again, very innocent parameter in front of the interaction. Now, I want to emphasize that there's another miracle here. Because in general, if you have some matrix dynamics, then it's very unlikely that when you project it onto eigenvalues, it will still have a Markov process. Here, not only you got a Markov process, but actually quite easy one. Solution of very explicit stochastic differential equation. So beta has the same role as before. And again, these can be extended for any values of beta larger than 0, right? You look at the solution of exactly the same equation. Well, you need to prove something. You will need to prove that this equation indeed has a solution for other values of beta. But this can be done. A little bit harder for beta approaching to 0, but still people did it. So that's a second way how you can add second dimension to these matrices. So these Dyson-Brownian motions, why they were started, Dyson himself introduced Dyson-Brownian motion because he wanted really to add time to this random matrix distribution. So somehow there was an interplay for him between equilibrium statistical mechanics and non-equilibrium statistical mechanics. So he wanted to connect these two areas together. And that's how he introduced this evolution. Well, since Dyson, Dyson-Brownian motion found its applications in many areas of random matrix theory and adjacent probability theory. So it was used as a tool for proving universality of eigenvalue statistics. Somehow, if you want to analyze single matrix, then it's very helpful to view this matrix as, maybe to start Dyson-Brownian motion for this matrix and see what's happening there. So it was also at beta equals to 2 that was a central tool in study of interface growth models from so-called Arpa-Rizzi-Junction universality class. And the last point I also want to make that's kind of interesting one. So if you study models of statistical mechanics such that maybe Ising model or self-avoiding walks or other models, then very often in these models of statistical mechanics you have some interfaces. Maybe in Ising model that will be interfaces which divide pluses from minuses, or something else, various interfaces. And these interfaces very often in the scalar limit become conformally invariant objects, and then these conformally invariant objects are encoded through the theory of Schramm-Loeffner evolutions. And there is a theory of these Schramm-Loeffner evolutions when you have kind of several interfaces evolving together. And in these several interfaces evolving together is something called parameterization for these interfaces, or driving function. And this turned out to be exactly Brownian motion, Dyson-Brownian motion, well, solution for that equation. And what's interesting here is that in this way, in the statistical mechanics models, values of beta which are different from the classical 1, 2, and 4 appear. For example, you can get beta equals to 8 or beta equals to 3, depending with what models you work with. OK, so that's a second object, this Dyson-Brownian motion. So we have two objects, two-dimensional objects, right? We have these corners processes, and that's a simulation for the matrix of size 10. And we have Dyson-Brownian motion, that's a simulation for 5 particles. And what do we want to do with these objects in my talk? Well, generally speaking, we want to understand the asymptotics of these objects when n is very large, so when your matrices are huge, but the parameter beta is fixed. So maybe you take beta is equal to 13, and you take n equal to 1,000 or 1 million, and you look at the evolution of these eigenvalues in either of these processes, and you want to understand, OK, what's happening with this evolution. So that's our task. Now, one result about this evolution is a very old one. Well, it's kind of hard to say what is the exact reference here. So Wigner knew some parts of it, but then maybe other people gave further improvements. So this will tell you something of the following sort, that you see on this picture, there is this border between the part of the system where you see particles, so eigenvalues, and the part which you don't see these particles. And then the claim is that this border is exactly a parabola. So namely, if you look at this corners process, that will happen is that you draw a parabola where on the vertical axis you have n size of the matrix, and on the horizontal axis you have your eigenvalues, and that's the parabola here. And the largest eigenvalue will be sticking to the right side of the parabola, and smallest eigenvalue will be sticking to the left side of this parabola. And similarly, if you have time evolution of Dyson-Brownian motion, there is kind of slightly different parabola, but again a parabola, and again everything stays inside this parabola. And if you want to connect to the topic of this conference, then really you can say that it is some kind of a strong convergence towards semicircle law, because that's again about the norms of these matrices. So that is an old result. People in the community knew it like forever. Now, what was not known for a long time, that was how to describe the scaling limit of random curves of eigenvalues near this parabola. You're kind of saying that in first order you converge to parabola, but what if you look at fluctuations about this parabola? Clearly, this curve, well, it has still some randomness here, and you want to describe this randomness. These curves near parabola, what do they look like? How to describe them? So that's the question which I'm addressing in my talk, how to describe, the scaling limit of these random curves near your parabola. Okay, so here's our theorem then, that if you look at the rescaled largest eigenvalues of Gaussian beta corners process or Dyson-Brownian motion in a small window near your parabola, so maybe here or maybe there, then they converge as n goes to infinity to is exactly the same limiting object. And this object, that's what we call Airy-beta line ensemble, or LAE-beta. Well, the name, what is Airy here? So the origin is that many formulas for this object can be written in terms of the Airy function, which is the solution of this, second-order differential equation. Okay, so I haven't defined yet for you what is this Airy-beta line ensemble, and I will try to tell you a little bit about it. But first of all, something that might surprise you is, why is even this limit the same in these two problems, right? Because that was about cutting corners from matrices. That was this Dyson-Brownian motion was kind of about adding matrices. So why should these very different algebraic operations, cutting corners and addition, lead to exactly the same scaling limit? And, it's a little bit hard to say. So, I don't have fully satisfactory answer to this question, why addition and cutting corners brings you exactly the same objects. But my answer to this question would be that, well, in fact, exactly the same object should also appear in many other problems. Namely, this Airy-beta line ensemble, which we saw in the limit, which is this infinite collection of random curves, which you see near the edge. So we expect it to be a universal object, which appears in many, many, many different problems. So maybe there is hundreds or thousands of problems in which you can find Airy line ensemble. Okay, we just found the two first ones where this appears, but there will be many others, looking forward. Now, if you look at some marginals of this Airy line ensemble, that some parts of its universality are actually already known in the literature. For example, if you look at the largest eigenvalue at fixed time, so this orange thing in the middle, just distribution, one-time distribution of one position. So that is something that will be called Tracy-Widom beta distribution. And it is already known to be universal. It appears in many different problems. At beta equals to 1, it appears in the scaling limit of largest eigenvalues for real symmetric matrices, adjacency matrix of random graphs, some statistical texts, some growth model from Kadari-Parigi-Zhang's universality class. For beta equals to 2, similarly, you have some complex Hermitian matrices and their largest eigenvalues, some random partitions and random timings models. So many things where you see this Tracy-Widom distribution already. If you look at the fixed time and all particles together, so you kind of draw a vertical section on this picture, then it's known that these eigenvalues, they will be given by the eigenvalues of an object called stochastic area operator, which again appears as a scaling limit of several classes of probabilistic models. When beta is equal to 2, then this area line 2 ensemble is a central object in the KP's universality class of interface growth and interacting particle systems. So again, it appears in many situations. So kind of particular marginals or instances of that are already known to be universal, but we hope that the full object is also somewhat universal and appears in many situations. A little bit of history, what was known before our work about this area line ensemble. So people were obtaining similar theorems about the appearance of this ensemble at very specific values of beta. So maybe the oldest results are about beta equals to 2. So these are complex Hermitian matrices where people were already for the last 25 years were obtaining results about convergence to the Airy line ensemble. And more recently, beta equals to 1 was analyzed through the moments of Wigner matrices. Then 5 years ago, I had a result with Victor Clepson about beta equals to infinity. And there was a series of results of different people where people try to analyze in what sense can you make sense of this Dyson-Brownian motion as an SDE in the limit of n goes to infinity, and how to make sense of
What does
that.
beta equals infinity mean here?
What?
What does beta equals infinity? What object is that?
There will be a slide on that, so you will see it right yet. I will go more details.
In your formulas, it didn't seem to make sense, right?
Well, you can kind of send Dyson-Brownian motion just makes sense at beta equals to infinity, right? It just, well, you need to rescale. You need to rescale a little bit, right? Yeah, I will come to that, right? So, compared to these, results, so what is our key development? So our key development is that we covered all beta positive in kind of uniform way, and both Dyson-Brownian motion and Gaussian beta corners process, and more importantly, we managed to somehow construct this limiting object. Because if you think about like what is the main challenge in analyzing these scaling limits? Well, the main challenge is that your limiting object is this infinite collection of paths, right? So it's very infinite dimensional object, infinite dimensional random object. So how do you describe this infinite dimensional random object? What is the right language to use it? And that was a difficulty, finding some language which will work for description of this Airy-beta line ensemble. Okay, so what is our description? So in our paper, the description of this limiting object is given by the following language. So, you have your collection of random curves, this A. So you first start by taking a parameter z and looking at the vertical section of the picture, and then computing some kind of a Laplace transform of the positions of particles. So you sum over all particles over vertical section exponent times z times position of this particle. So this is an infinite sum. So z needs to be positive in order for these to have any chances of convergence. But then it's actually convergent. So there's exponential decay. There's a convergent sum. But this sum is, of course, still a random variable, right? So it's not deterministic. That's a random thing. So this random thing we describe in the limit with joint moments. So we have, you vary t, you vary z, and you look at the joint moments of these random variables, and that's how a limiting object works here. So it's a little bit non-trivial actually to see that these joint moments uniquely determine the ensemble, because actually the moments grow very fast in this situation. But you can use some additional arguments to convince yourself that that's what's happening. Now the formulas for these joint moments, they are not super easy. So I will only show you one of these formulas, which we got. That was a formula for the first moment when m equals to 1, just expectation of this expression. So this formula will involve certain integral over what? Well, there will be a space of some step functions, which are kind of schematically shown on this picture. So these are functions which are making some jumps up and some jumps down, and you kind of integrate in respect to positions when these steps up and down are happening. And on top of that, there will be a Brownian excursion, which kind of lives on top of all these functions, and you compute some expectation with respect to this excursion, which is very explicit in this situation, like all things are known about the excursion, and then you integrate with respect to these positions. So, not the simplest formula, but somehow a formula which you can put into your computer. And also what's important is that the beta parameter just enters in the formula in just very innocent way. So in particular, everything is completely analytic in this parameter beta. You kind of treat all betas in completely uniform way. Okay, so that's our description in terms of these random Laplace transforms of this Airy-beta line ensemble. Well, that's not an easiest description, so it's natural to ask, okay, are there any simpler descriptions? And for general beta, we don't know simpler description, but for some particular values of beta, actually, some other simpler descriptions were known before our work. And let me mention some of those. So for beta equals to 2, for the complex matrices, there are two alternative descriptions which you can find in the literature. One of them that is through correlation functions. So namely, if you ask yourself what are the probabilities that your particles, your lines go through some collection of points, then this probability can be computed as a determinant of a matrix. So if you have a 3-point, that will be determinant of 3 times 3 matrix, and then the matrix elements, these are so-called correlation kernel. There's something explicit expression in terms of the Airy function. And that's how the first people arrived at this Airy-2 line ensemble. So alternative description, which is much more recent, is you can characterize this Airy line ensemble at beta equals to 2 through something called Brownian-Gibbs property. Turns out that if you look at your collection of paths and then you take some finite window and you erase everything inside this finite window and then you try to resample it back, then you can do it. All you need to do, you just need to resample this path as independent, non-intersecting Brownian motions conditioned to have non-intersections for each other. So maybe you have 3 of those, and you resample it as 1, 2, 3 Brownian bridges conditioned to be non-intersecting. And you can show, it's not very non-trivial theorem, you can show that this property actually uniquely determines your Airy line ensemble. Yes?
In this picture here, is the purple process also conditioned, is the purple bridge also conditioned not to hit the light blue bridge?
Yes, yes. So you need to condition on kind of, one, like maybe this blue line and, these 3 entry points. And then you condition on everything non-intersecting, right? So that's a very nice description, 2 descriptions at beta equals to 2. Unfortunately, neither of those extend beyond beta equals to 2. So nobody knows how to compute correlation functions beyond beta equals to 2. Nobody knows what is an analog of this Brownian-Gibbs property beyond beta equals to 2. Another description, answering Ramon's question that we obtain, a very explicit one, that's about beta to infinity. So in beta to infinity, you look at your Gaussian beta corners process, the same as before. And now you look at the joint limit, in which you will be sending n to infinity and beta to infinity together. Now, in the first order, if you look at the particles of Gaussian beta corners process, then it turns out that they concentrate near the roots of Hermite polynomials. So there is kind of crystallization, if you want. They become completely deterministic. But if you subtract these roots of Hermite polynomials and rescale back by square root of beta, then there is some field of fluctuations. And it turns out that there's explicit Gaussian field, explicit in the sense that it's a Gaussian field with explicit covariance, which you get in the limit of joint, n to infinity, beta to infinity. And here's this covariance. So certain explicit integrals in terms of the Airy functions and the zeros of the Airy function. So AI here, that's a ith 0 of the Airy function. And how should you think about it? Well, really, the way to think about this formula is that this is some kind of a first 2 terms of the Taylor series expansion of your Airy line ensemble as beta goes to infinity. So the very first term, these roots of Hermite polynomials, they just turn out into the roots of the Airy function. So all your lines will be just constants at the root of the Airy function. And then on top of that, you have some explicit Gaussian field with explicit covariance. So these are kind of the first 2 terms in this expansion. But actually, that's not that bad. If you compute some numeric characteristics at finite value of beta, even beta equals to 1, then you can get some good matches just by using this approximation from beta to infinity. But again, these are only first 2 terms. We don't know how to move further to get something simpler than what we had from previous theorem. Well, there's also conjecture in the literature, which is unlikely to be true, but if it were true, that would be an amazing description of this Airy line ensemble. Namely, what is well known by now is that if you fix time here, again, draw a vertical section of this picture, and you look at the joint distribution of particles along this section, so this is just a single matrix for which you look at the distribution of largest eigenvalues, then that is given by the eigenvalues of so-called stochastic Airy operator. So there is a 2nd order differential equation which acts on the half line, so the positive half line, and which has, okay, 2nd derivative minus x. Okay, that's a little bit nasty object, white noise, but you can make sense of it in this situation. And again, beta enters in a very innocent way. That's just a prefactor 2 over square root of beta. So that works, for fixed time. Now, we have not a fixed time. We have a whole process which evolves in time. So you kind of want to add time dimension somehow to this white noise. And the question would be, is there a way to do it somehow? So there were some conjectures, actually, last year in the article of Edelman, Jung, and Nissim, we say, okay, what if we do just in the most naive way? Well, you need to have some stationary process here. So maybe you just extend this white noise as the Ornstein-Uhlenbeck process in this time dimension. And you try to do that. So that was a conjecture which they stated. But actually, in the same article, they kind of said, no, it's unlikely to be true because they made some numeric simulations. They were a little bit inconclusive because it's kind of hard to simulate these objects. But they were more inclined to say that the conjecture is more likely to be wrong. And then our paper appeared, and the paper of Jiayang, Huang, Lingfu Zhang, another one which also the formulas do not seem to agree with this conjecture. So probably it cannot be that easy, but still the question remains: is there any way to extend these white noise in time somehow so that you will get our Airy line ensemble? And it's kind of very unclear. So for example, what this paper suggests, that if the conjecture is wrong, then it might be true that even your object your noise should be non-Gaussian jointly. Like for each time it might be Gaussian, but jointly for several times it's unlikely. It's unclear whether it should be Gaussian or not. But if something can be done there, I think that would be fascinating description.
What does not seem to agree formulas mean? Like does not seem to agree. It means like.
Well, you compute with one side, you compute with the other side. They seem to be not matching, but maybe there is some, tricky transformation, right? Maybe we just missed some, simple. So, I don't like to say that no, right? Maybe there is some simple transformation which recover the things, but we couldn't find it, and the formulas do not seem to be similar. Yes.
Does the Brownian and Gibbs property characterize the Airy-line ensemble?
For beta equals to 2.
Yeah.
Right.
So is that the unique kind of stochastic process with a bunch of
Yeah, so there is a recent paper. There was a paper of Amol Agrawal and Jeong Huang, 2 years ago, 300 pages paper where they proved that there is a unique process. I think it's under review, but hopefully it's correct.
So Vadim, for general beta, do you have a spectral interpretation of the Dyson-Brownian motion? Is there some, for example, dynamics of tridiagonal matrices?
No, that's exactly what Edelman is trying to do. So in their paper, they take Dyson-Brownian motion, then you can tridiagonalize it for each moment of time. But the problem with that tridiagonal matrices, they evolve in very, very complicated way. And that's what they're trying to do some edge limits, and they seem to be failing kind of to understand.
It appears in this dynamical picture that you depart from spectral theory as soon as you go to beta. That's not 1, 2, and 4, even though that's not true for the Barnes units.
I don't know. It depends what you call spectral theory, right? So there is no proper matrices. You're right. So there are no proper matrices for which you compute eigenvalues. Yes, that's true, right? Because there is no field of dimension beta, right? So you need to extrapolate away from it somehow, right? Okay, so let me tell you a little bit about toolbox, because I think that's interesting by itself, and also it connects to things that people in this audience might have done in their life. So our main toolbox, which allows us to do something, is so-called Dunkel operators. So what are these creatures? So these are different/differential operator. So there is an operator which will be acting on functions in n variables. And how does it act it? So you have n variables y's. So you differentiate with respect to one variables. And then you also have a difference operator. So 1 minus ij, where ij, that's a transposition. That's something which interchanges the variables I and j. And then you divide by yi minus yj. And beta, again, just enters as a prefactor here. So theorem, if you take Gaussian beta ensemble, so just, fixed time, fixed size object, and you compute its expected moment. So if it were the matrix, that would be expectation of the trace of the kth power of this matrix. Then this can be expressed in terms of the action of this operator, kth power of this operator, on explicit function, just exponent of the sum of the squares, after you act, you plug in all variables equal to 0. Now, if n were equal to 1, then I claim that everybody in this audience would be able to prove that, because that's actually, you just have Gaussian distribution, and you're just trying to extract moments of this Gaussian distribution by differentiating its Laplace transform, right? And everybody knows that's how you do, right? That's what you learn in probability classes. So it's kind of standard property. But the trick is that this is still true for n larger than 1. But now it's not just derivative, but this quite weird-looking operator which becomes necessary. And you need to know a little bit of representation theory to prove that. You need to know theory of multivariate Bessel functions to prove that. And there are lots of generalizations of that. These generalizes to multi-time, multi-level, all kind of things. This formula would generalize there. And combinatorics of this formula, that's a key to all our asymptotic results. So just analyzing combinatorics of applying this operator to these functions. Now, when I say combinatorics, what kind of combinatorics? So let me again connect to something that people in this audience probably know. Namely, I will connect to the semicircle law, which appears in the limit of the Gaussian beta ensemble. So let's try to prove, using these Dunkel operators, the following identity. So if you look at the 2kth moment of your matrix, and you rescale it properly, then it converges as n goes to infinity to the kth Catalan number, which is, of course, just the 2kth moment of the semicircle law. So using these Dunkel operators, it's not that hard. So omitting some details, what essentially is happening is that you are just, you're applying this operator, its power, to this exponential expression. So when you apply derivative, and what's happening is that the derivative applying to exponent produces factor y for you, right? It kind of grows the degree of the prefactor. On the other hand, this thing, it doesn't grow degree. Instead, it decreases the degree. So you have this kind of creation operator which creates y's, and then there's this death operator which kills y's. And OK, if you killed everything too many times, then you are just dead. Like, then you get in 0. So really, you want not to kill too many things. So in terms of these actions, what it means is that you want the monomial to stay with non-negative degree. So if you think about these derivatives as up steps and these things as down steps, then essentially what you want to see these up-down walks which stay positive. And now that's precisely the definition of Catalan numbers. And in this way, from this formula, very quickly you see that Catalan numbers appear in the limit. And then our asymptotic analysis is really fancy realizations of that. So now actually you will need k also to be growing with n. That's what gives you access to this largest eigenvalue. So these expressions become much more complicated, but eventually we're able to analyze those, and that's what gives rise to our asymptotic formulas. OK, good. So time to summarize. So what we have seen today, so there is this Gaussian beta ensemble, Gaussian beta corners process, Dyson-Brownian motion, hopefully central objects of random matrix theory. So we analyze their edge limits, obtaining this Airy-beta line ensemble. Well, we got it for 2 models, for corners process and for Dyson-Brownian motion, but we expect that this is really a universal theorem. So many other random matrix models, and maybe not only random matrix models, should have similar limits. And let me end with maybe one point of advertisement. I was working for many years on these beta ensembles, but maybe people in the audience are not that convinced. Why should you even study beta ensembles, right? Why should you go beyond beta be equal to 1, 2, and 4? And I have 2 arguments why you should be doing that. Well, one argument is that it kind of doesn't make sense to redo whatever you have for real matrices, then again for complex matrices, just do 2 completely different proofs. So you want to have some unified approach which will cover both situations. Another thing which I kind of discovered when given classes in random matrix theory is that like 50 years ago, people developed special theory to study beta equals to 1 real ensembles. That was a theory built on the Pfaffian point processes. But somehow at this point, the theories which people develop for general values of beta is already simpler than that theory based on Pfaffians for beta equals to 1. So somehow, even if you only care about real matrices, that if your ensembles are such that they admit general beta extensions, then actually it's better to use general beta tools that will give you simpler results and simpler arguments. And for my talk, that's it. Thank you.